Hello, I'm Dragan Maksimovic. I'm a professor at the University of Colorado Boulder, and I am pleased to present this short introduction to soft switching in switch mode power converters. In this short video, we'll try to clarify the concepts of hard versus soft switching, zero voltage switching, resonant transitions, zero current switching, and how all these relate to loss mechanisms in switching power converters. We'll do all that on a very standard structure. It's called half bridge, consisting of two devices supplied from a DC bus. And we will do that on an example of a half bridge representing a synchronous buck DC-DC converter. The control waveforms for the half bridge are shown on the right hand side. You have a pulse width modulated control signal C. That control signal is split into two non-overlapping control signals for the main control FET Q1 and the synchronous rectifier Q2. And between the two control signals for the two MOSFETs, there are short gaps called dead times that ensure that we never have a cross conduction or simultaneous conduction between these two devices. We will be talking about the half bridge with silicon power MOSFETs, but really the same discussion or very similar discussion holds for other device types. Before we get into details of the switching transitions, let's take a quick look at the MOSFET structure and some of the parasitic elements around that MOSFET structure. So first of all, the conduction between drain and source is controlled by gate to source voltage. When the gate to source voltage is well above threshold, a conductive channel is established between drain and the source, and the device is represented by a relatively small on resistance. Around the device, we can represent these parasitic elements as capacitances, gate to source, gate to drain, and drain to source. And we all know that the capacitance, the output device capacitance and the gate to drain device capacitance are highly nonlinear with respect to the drain to source voltage. In addition, importantly, the device contains a built-in body diode. That body diode is effectively present between source and drain terminals, and we show it explicitly here, understanding that you cannot just take that body diode out, it is part of the device itself. So let's look at a particular example. So we'll do some simulation examples to illustrate the concept. So this particular example is a 48 volt to 12 volt DC-DC converter, a synchronous buck DC-DC converter operating at 500 kilohertz, and the operating waveforms of the inductor current and the switch node voltage right here are shown in the waveforms here. So inductor current is a familiar triangular wave shape, here shown with relatively small ripple around its average value of 10 amps, which is the load current. The switch node voltage is a pulsating waveform, the duty cycle of which is really determined by the control duty cycle for the half bridge. So now we want to find out what is happening at these transitions, right? We are turning off Q2 and turning off Q1 or vice versa. These transitions are critical to understanding what we mean by hard versus soft switching, and we'll examine those in some detail now. First, let's look at the Q1 turn off to Q2 turn on transition, as we are zooming in here on the control waveforms for the high side Q1 switch as being turned off here, followed by a dead time that's relatively short. And after that, we have a turn on of the low side switch or the synchronous rectifier. So what happens now with the current that is going through the channel of the device Q1, and what happens with the voltage across that device? The current and the voltage of the device are going to be able to tell us what is happening in terms of the losses across the device during the transition. So first of all, we are starting off with a current that's not equal to zero. This is going to be a non-zero current switching turn off. From that point, the channel current through the device is going to drop down towards zero. And during that time, as the current through the device is now lesser than the current that is going through the inductor, we have now current that is charging and discharging the capacitances of the switch node, and in response to that, the drain to source voltage of Q1 is going to start increasing up. Once the current has dropped down to zero, then the switch node voltage continues to increase because the capacitances are being charged up or discharged until we have the D2, the body diode of Q2 turning on. At that point, we can turn on Q2 and we have the final state after the transition. So let's look at the nature of the transitions here. So first of all, we say, hey, Q1 is not turning off at zero current. Okay, so there is potential for switching loss. And indeed, during this first time interval, it's relatively short. For silicon MOSFETs that are relatively low voltage, this would be in the order of maybe 10 nanoseconds or so. There is an increase in the VDS voltage, and because of the simultaneous presence of the channel current and drain to source voltage, there is going to be a switching loss present. The switching loss is relatively small because the voltage is increasing relatively slowly as the current is dropping down, and that slow increase in voltage is determined by how fast we are charging the switch node capacitances. That consists really of a parallel combination of the output capacitance of the two devices and any other maybe trace capacitances that you have with respect to the circuit ground. So the way we would characterize this particular transition for Q1 is that it is non-zero current switching, but it is approximately ZVS because of the device capacitances that are helping us, and that's why we have relatively small switching loss. Q2 turn on at this point here is entirely ZVS, right? You have a very small voltage across the conducting body diode, and you turn on Q2 at essentially zero voltage, so there isn't much of any switching loss really associated with that particular transition. Okay, so that's what we have during Q1 turn off to Q2 turn on. Let's look at the opposite transition. Q2 turn off to Q1 turn on transition. So first of all, here we are going to look at again the IQ1 and VDS1 waveforms. When Q2 is turned off, the body diode is going to take over the inductor current, and the voltage across the top switch, the main control switch, is going to slightly increase because of the body diode conduction of Q2. During that time, the Q1 is not turned on yet, and so the current remains equal to zero. We finally turn on Q1 at this point in time, and that is going to result in the current of Q1 ramping up as a function of time like this. What happens with the diode D2 during that time? Well, as long as the current IQ1 is lesser than the inductor current, the diode D2 is still conducting, and so you're still going to see a diode voltage drop across the body diode of Q2. Now, as the current reaches the inductor current, you would hope that diode D2 is going to turn off instantaneously. Unfortunately, it doesn't because of the need to perform a reverse recovery of diode D2. And the result of that reverse recovery is going to be a very large spike in the current IQ1 well above the inductor current, ultimately coming back to the inductor current. But during that transient, we are going to have a significantly larger current spike through Q1, and the area under this curve here is going to represent what is the reverse recovery charge of the diode, diode D2. That's the body diode of the synchronous rectifier. The whole process is going to end up around here, and during that time, the voltage is going to remain as if the diode D2 were still forward biased until it eventually gets to the point where it's reverse biased and the voltage can start dropping down towards zero, completing the transition. This transition here is particularly troublesome because it involves a substantial amount of time when the product of these two quantities, the IQ1 and VDS1, is very large, and we have the net effect being a large switching loss. In fact, this is the largest switching loss mechanism present in the hard switching converter. This is what we can say here is at this point here would be the hard turn on of Q1, and that hard turn on incurs large switching loss because of three mechanisms. One is the fact that it takes time for the current to ramp up. The second is the reverse recovery of the body diode of Q2. And the third is this transition in voltage here really amounts to lossy charge and discharge of the switch node capacitances. So these three mechanisms together, the most important one of which is really the reverse recovery of the diode, contribute to relatively large switching loss associated with hard turn-on transition of Q1. At the same time, you can go back into Q2 and say, hey, this is going to be ZVS. There are no issues there. ZVS of Q2 is just transferring current from the channel of the device to the body diode. That's not going to incur much, if any, really switching loss. All right, so here's the simulation waveforms again with the noted transitions. We have ZVS turn on and turn off of Q2. We have non-zero current switching turn off of Q1, but the switching loss is relatively small because the voltage increase across Q1 during that time is relatively small. And the main hard transition is really the Q1 turn on at non-zero voltage, accompanied with the reverse recovery of the body diode of the synchronous rectifier switch. So here's a summary of what we have in terms of hard switching for a half-bridge configuration. We're looking at this in the context of a synchronous buck converter, but the exact same conclusions follow for half-bridge used in any number of converter structures. This is a very, very common configuration. If the inductor current here is positive, Q2 is going to experience zero voltage switching turn off and zero voltage switching turn on. Q1, on the other hand, is going to experience non-zero current switching turn off, but that results in relatively low switching loss because the increase in voltage is relatively slow. The turn-on transition of Q1, unfortunately, is producing a large amount of switching loss. This is the hard switching transition at non-zero voltage, and the reverse recovery of the opposite switch diode is what really makes the switching loss extremely large. As a simulation example, let's look at some numbers. Here we are using FETs with 3.4 milliohms of on resistance. We are supplying 10 amps at 12 volts, about 120 watts of output power, and we are switching at 500 kilohertz. The conduction loss is just the on resistance of these devices times the RMS current of the inductor, and that comes out to about 0.3 watts, relatively small conduction loss. Switching loss, on the other hand, is very large. It's more than 10 watts. In addition, there is a gate drive loss associated with turning on and off Q1 and Q2. That amounts to about 1.5 watts for a total loss of more than 12 watts and efficiency of about 90%. The simulation here includes only MOSFET losses. Of course, additional losses would be in the magnetic components and other miscellaneous losses around. All right, so now let's examine where this hard switching problem is really originating from. The root cause of hard switching is that prior to Q1 turn on, the inductor current is positive, and the body diode D2 of the synchronous rectifier or the bottom switch is conducting. Thereby, upon turn on, the voltage across Q1 is large, and we have a non-ZVS turn on that produces significant amount of switching loss. So how can we mitigate this? What can we do to make this root cause of the hard switching problem go away? Well, how about we think about ways of reversing the polarity of the current just prior to Q1 turn on? How do we do that? In this particular example here, there is a very easy way to do that. We can simply make the inductor current ripple be large enough so that prior to turning on Q1, we reverse the polarity of the inductor current, and we use that negative current in the inductor, energy stored in the inductor, to produce what is called a resonant transition, to charge up the voltage at the switching node from essentially zero to the point where the body diode of the top control FET is conducting, and do that in a resonant manner and thereby facilitate zero voltage switching of Q1 as opposed to this very lossy non-ZVS switching of Q1 that we had in a hard switching converter. This particular mode of operation is called zero voltage switching quasi-square wave mode of operation. Let's look at the details of that critical transition now in this soft Q2 turn off to Q1 turn on. Now we are going to have the voltage across the FET Q1 start from the voltage that's equal to the DC voltage here, but it can transition immediately because the current is now flowing in the opposite direction. So instead of having the current communicating to the body diode, that current that is now negative through the inductor can charge up the capacitance at the switch node and result in a voltage transition that is resonant in nature. So that voltage transition is going to look something like this. We have a resonant transition here until we get to the point where the voltage across Q1 drops to 0 and the body diode D1 of Q1 starts conducting. After that, at the point when we turn on Q1, we can do that at zero voltage, and we're mitigating this major loss mechanisms. What happens with current IQ1? Well, the current IQ1 is going to start ramping up to the inductor current right here. When you now look at these two waveforms, you see that between the two there is essentially no overlap, and during this transition here we'll have approximately zero switching loss. This transition here is called resonant transition, and it is called resonant transition because it is facilitated by the resonance between the inductor L and the switch node capacitance. That's the resonance that is described by this waveform here, dropping VDS voltage from the DC voltage down to 0, upon which we can execute a zero voltage turn on of Q1. Right. So now in the soft switching case, here again the full set of simulation waveforms. Q2 has a ZVS turn on. It has a turn off that's close to zero current, and so it exhibits this near zero current switching and near zero voltage switching turn off with very low loss. And then most importantly, we have a zero voltage switching turn on of Q1. We have mitigated the major switching loss mechanism in the hard switching converter. At the same time, I want to bring to your attention that Q1 is turning off at non-zero current, and in fact it is turning off at a current that is larger than the current we had in the hard switching case. So this is going to incur some amount of switching loss, but still that loss is going to be relatively small compared to the hard turn-on loss that we observed in the hard switching converter. So here is a summary of the switching loss mechanisms for Q1 and Q2 in the soft switching case. So turn off, again, it's near zero current switching, near zero voltage switching, very low switching loss. Zero voltage switching turn on of Q2, and then as far as turn off is concerned, we have a non-zero current switching, but still relatively low loss, although somewhat higher compared to the hard switching case. And then most importantly, we have a turn on at zero voltage switching, and that's the main benefit of this type of soft switching. Here is the simulation example again for the soft switching case. All right, so conduction loss now, as you can see here, is actually a little bit higher. From 0.3 watts we go to 0.6 watts. Why is that the case? We have a larger amount of current. RMS current through the inductor is larger, and the conduction loss is larger. On the other hand, the benefit of soft switching is that the switching loss is now much smaller, the total loss is much smaller, and the efficiency is much improved compared to what we had in the hard switching case. All right, so in summary, we can conclude that ideal soft switching amounts to turning on a device when the voltage across its terminals is essentially zero. That's the best possible situation for turning on the device. Zero voltage switching is the best soft switching mechanism for turning on the device. In terms of turning off, the best case is to have low current at the time when the turn-off occurs. So having close to zero current at turn-off is beneficial for reducing the turn-off switching loss. Benefits of soft switching include much reduced switching loss, potential to improve efficiency, potential to operate at higher frequency, maybe reduce the size of magnetics and thereby increase power density. And in addition, we have waveforms that have less electromagnetic interference potential, so reduced electron EMI is another potential benefit of soft switching. We should be aware of the fact that soft switching is not necessarily free benefit, right? There are potential side effects. Those potential side effects include perhaps higher voltage or current stress on devices. In the example we discussed, we found that the currents are now actually higher at the point where the transistor is turning off. Also, the RMS current through the inductor and through the devices is increased, and so there is going to be an increase in conduction losses. Finally, there is also a potential for having increased AC losses in magnetics if we have a larger amount of AC currents going through the converter structure. These benefits and potential side effects depend on the converter topology and operating mode. They differ between different options we have available. There are many options, and there is ample room for innovation in the area of soft switching converters. Finally, just to mention a few references, a general reference for the switching mechanisms, we have our textbook. And then on this particular method of soft switching that's referred to as zero voltage switching quasi-square wave mode of operation, I have the original reference that comes from APEC 1988. There is a little bit more detail on the design of that particular option. And then there are more recent references on these particular techniques, and there are different names used for essentially the similar or same effects. So the technique has actually been relatively popular and it's used in practice. I should mention again that we have many different options in terms of soft switching converters, and this example presented today is just one particular example trying to clarify the nature of switching transitions and where these switching transitions come in terms of characterizing losses in a converter. Thank you.